Hello everyone. I welcome you all for today's session on digital system design using Verilog. Lecture 5 on Module 1, Introduction and Methodology. If you're not subscribed to my channel, subscribe to my channel for further notification. Today, we'll be seeing two important concepts. That's on verification of combinational circuits and the number systems. Number systems we are already familiar, but then too, we'll just go through the concepts. So verification of combinational circuits. Here, there are small scale applications where combinational circuits are sufficient. So we will show how we can apply our design methodology to them. So what is the concept here is that we have seen some of the important concept in the earlier class that's about models, design methodology. And we have seen the block diagram and what are the different stages are involved in designing the model there. Now we can apply it for even the small concepts. There's a small model consisting of a combinational circuits. Okay, so how this particular design methodology will be helping us in designing the combinational circuits is very, very important. Now, in the combinational circuit, what we do here is that whatever the input we are giving it to the combinational circuit as an input, the immediate effect is on the output. There is no feedback present in the combinational circuit, or there is no clock signals present in the combinational circuits as we can analyze it there. So when clocks and feedback comes, then it becomes a flip-flops. So without flip-flop, whatever the components what we have, or all the basic blocks of combinational circuits what we have studied, like decoders, encoders, multiplexers, some of the examples of the combinational circuits, along with some of the basic gates and everything. Okay, now once we design that, what we have to do? We have to verify the functionality there. So we have in Verilog one important method to verify that particular model is by writing a test bench. What is a test bench? The test bench that stores the input values and acts like an input to the design under verification. Means a model which has to be verified. For that model, the test bench will give an input, and the respective outputs are verified with the help of a simulator or any other method what we have there. But now, since we have studied about simulators and we have seen practically also the model thing, so let us say that we can see the output at the simulator. Sometimes design under verification is frequently called as device under test, DUT. So the model which we are writing, the program need to be tested correctly whether that particular model is satisfying the required constraints or meeting the required specifications. So what is that? Whatever I'm giving the input, it should produce the respective output and meeting all the constraints. One is timing, area, power, performance, cost, basic 5. Okay, so that's the important thing when you are designing the model you have to think. So test bench model itself is a Verilog model that we can execute using the simulator. As I said, we are storing all possible configuration of the input of a model. We are writing the program in the Verilog. We are giving as an input to that. It means that we are writing the test bench and instantiation, or we are calling the model and feeding the input to that particular model and checking the output, whether it is producing correct output or not. So that's the thing what we have. The purpose is to apply a sequence of values called test cases. So all possible input configurations are called as test cases to the input connections of the DUV and to monitor the output connections to ensure that correct values are produced. So this is the basic important thing what you must know there. So the default part of developing a test bench model is working out how to express the correctness condition. See, when we are writing the test bench, it's not compulsory that it is working properly or not. But you have to make sure it meets all the design constraints here. If the requirements are expressed as a Boolean equation, the design will be probably implemented those equations directly by using data flow model, that is by using the assignment statement. One simple example here we have in the examination, we have this question there. Develop a test bench model for the light controller and enable model for a traffic light control circuit. For controlling the traffic light, we have to write the test bench model there. So verify the conditions that when the enable input is 1, the output is the same as the light input. And when enable input is 0, all light outputs are inactive. It means what? When enable is 1, whatever we are giving input, that should be the output. But when enable is 0, all the light should be inactive. So what we have to do is that the test bench model includes an instance of the design under verification as well as code to apply test cases to check for correct outputs. The organization of this component is as shown. If you observe the model now, see, this is the simple design methodology. There is a DUV. Assume that this is a light controller which is controlling the light. And the input to this is enable light sign. When enable is 1, whatever the light is there, that is passed on to the light out. This is the model what need to be verified. Now, all possible test cases are given in the test bench here. This is the test bench model, which is giving as an test case as an input to the design under verification. Now, this will execute the input whatever it is receiving and produce the respective output depending upon the conditions what we have there. Okay. Now, since the test bench is a Verilog model, it needs a module definition. So how to write the test bench? We have to write the Verilog model. When we write a Verilog model, we need to define a module there. But there will be no input specified here, because if you observe in test bench, there are no input to this. So there are no external connection to the test bench. The model has no ports. So test bench doesn't have any ports. So now let us see the program for this. The module definition is for the particular light control what we have. So if you observe here, module light underscore test bench. So I am writing the model name and testing that the light is working or not. So here, if you observe, there is no ports present in this, but we are using the instantiation. If you observe, light underscore controller underscore and underscore enable. So this is the model which we are calling it. Okay. So once we call this, whatever the inputs are present here, same number of inputs will be used it in the wire there and registers. So output what we have in the design under verification is acting like a wire. Whichever the inputs are there, they are acting like a registers. So if you observe, positional mapping is one concept and port mapping is another concept. Now the way what we have written here is a port mapping. Okay, port mapping is nothing but here is not necessary to find write it in whichever the order. Once it is a port mapping, it is dot lights underscore out. Observe the same names we have bracket out for input and for enable. So what are the conditions? If you observe 3 or 4 conditions we have here, where enable is 0. When enable is 0, whatever may be the input, output is 0. Here input is 0, 1, 2, and 4. And what is this hash? 1000 is delay, nanoseconds delay there. Okay, or milliseconds. Now here in this it is milliseconds, so it will be in the terms of milliseconds there. Now, when enable is 1, light input is 3 tick B001. All the cases here, remaining 5 cases are having the light inputs. The respective light inputs will be displayed at the output after every 1000 milliseconds, because your time scale in terms of milliseconds, so it will be in terms of milliseconds there. So this is the actual test bench. So if you observe here, all possible cases of the light inputs they have given. It's not all. Here if you observe light inputs, since it is a 3 tick, all 8 can be used. Here they have used only 5. Okay. So here what happens is, after this we are just finishing it. So this is the initial values for the enable. Now to execute the program, always at enable or light in. So first what we have to see is that it should sense the change happening at the input, whether enable is changing or input is changing. If you observe here, enable is constant, input is changing. Here enable, once enable is changed after 4 values of enable as zeros, the 5, 6, 7, 8, 9 values are 1. Here the respective inputs is also changing. So the respective changes will be updated at the output. What happens when enable and light out, which is equal to light in? So what happens when enable is same, whatever the light out will be there, it will be same as light in. When enable is 0, the output is 0. Or display error in light controller. If nothing is happening there, you can display that there is an error in this. Okay, so this is how we are writing the test bench for the light control module. Okay, one of the example for the combinational circuit to display the lights depending upon the enable input. Okay, so this is one of the important concept what we have. Now let us concentrate on the number basics. Here we'll be covering unsigned integers, signed integers, fixed point numbers, and floating point numbers. First one is about decimal number, which can be represented as shown with an example of 124 to the base 10, where 1 is the 100th position, 2 is the 10th position, 4 is the unit position, which can be written as 124 to the base 10 is equal to 1 into 10 raised to 2 plus 2 into 10 raised to 1 plus 4 into 10 raised to 0. Similarly, we can represent the number in binary number systems where the base is 2. Now, same example we have taken, and we have represented the number in terms of binary, which is of 5 ones 0 0 to the base 2. If you see that 124 to the base 10 is equal to 1 into 2 raised to 6 plus 1 into 2 raised to 5 plus 1 into 2 raised to 4 plus 1 into 2 raised to 3 plus 1 into 2 raised to 2 plus 0 into 2 raised to 1 plus 0 into 2 raised to 0. If you add this number, we get the number as 124. Like 2 raised to 6 is 64, 2 raised to 5 is 32. So 64 plus 32 is 96. 2 raised to 4 is 16. 96 plus 16 is 112. 2 raised to 3 is 8. So 120. 2 raised to 2 is 4. 124. So in this way, we represent the number in the binary number format. So in general, the binary number system, a number x is represented using n bits, which is written as x is equal to x of n minus 1 into 2 raised to the power of n minus 1 plus x of n minus 2 to 2 raised to the power of n minus 2 x is equal to 0 to the 2 raised to the power of 0, where any number n can be represented with the help of n unsigned numbers there. Okay, so what number is represented by the unsigned binary number 101101 to the base 2? So you can observe here. So this is power of 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So 1 into 2 raised to 5 is 32. 0, it is 0. 1 into 2 raised to 3 is 8. 1 into 2 raised to 2 is 4. 0, it will become 0. 1 into 2 raised to 0 is 1. So when you add this, 32 plus 8 is 40, 44, 45. So for number 45 can be represented by 6 digits. How? Because if you substitute that n here, that is n is equal to 45, in the log 45 to the base 2, we get 6, because 2 raised to 5 is 32. So 5 digits cannot be represented. As 2 raised to 6 is 64. It is in between the 5 and 6. So highest number which is there is 6. So we have to represent that number with the help of 6 digits. So now we have taken a simple program for the Verilog module for the unsigned numbers. If you observe and develop a Verilog model of 4 to 1 mux multiplexer that selects among 4 unsigned 6-bit integers. It means what? The 4 is to 1 mux having 2 select lines and 1 output. But it is saying that 4 inputs is having 6-bit integers. So when it is 6-bit integers, so it should be represented in terms of 5:0. So if you observe in the program, in the multiplexer 6-bit 4 is to 1, output register 5:0 because it is 6-bit integer. Input 5:0, A0, A1, A2, A3, and the input select lines because 2 select lines. Always and the select line. So star is nothing but whatever you write in the sensitivity list of a case, it is select line. If it is 0, 0, Z will become A0. If it is 0, 1, Z will become A1. If it is 1, 0, Z will become A2. If it is 1, 1, Z will become A3. So this is a simple program of multiplexer there. So now let us study the octal number. So octal number is what? Here the base is 8. The number varies from 0 to 7. Here simple example of 253 to the base. So base 8 is equal to 2 into 8 to the power of 2, 5 into 8 to the power of 1, 3 into 8 to the power of 0, which is nothing but 171 in the decimal there. Okay. So 8 digits are 0 to 7, which is represented in terms of binary as it is. So if you observe 8, log 8 to the base 2 is nothing but 3. So 3 digit is required in representing in the binary there. So 0 is 000, 1 is 001, 2 is 010, 3 is 011, 4 is 100, 5 is 101, 6 is 110, 7 is 111. So this is octal number representation there. Similarly, now let us concentrate on hexadecimal number. Hexadecimal, the word itself says 16 digits because hexa is 6, decimal is 10. So 10 plus 6 is 16 digit number. So hexadecimal number is having the numbers from 0 to 15 there, where 0 to 9 is decimal numbers and remaining 6 digit numbers are alphabetical number, that is from A through F. If you observe here, A, B, C, D, E, F, which represents A as 10, B as 11, C as 12, D as 13, E as 14, F as 15 there. So this is the hexadecimal representation of the number in terms of binary there. And it requires 4 bits because log 16 to the base 2 is nothing but 4. A simple example of representing a hexadecimal number to a decimal is 3C is base 16. So it is 3 into, so the power of 3 is 2. So here, if you observe 3 into 16 raised to 2 plus 12 into 16 raised to 1 plus 14 into 16 raised to 0, and multiply and add it, we get finally 974. So let us concentrate on signed numbers. It is signed integer number. When we say signed integer number, here we concentrate on the sign of a number, that is a positive or a negative. When it comes to a negative number, in digital system, we know that we represent the sign number with the help of 2's complement form. And we already studied that in the basic electronics. We are not going into detail there, but in a simple way, how to understand that we can just check it out today. The difference is that for n-bit signed numbers, the weighted of the leftmost bit is negative. So how do we realize the positive and negative number? We know that leftmost bit, that is the MSB bit, is considered for representation of positive and negative number. If you observe here an example, two numbers are being given which need to be converted to decimal there. But if you observe here the MSB, this bit is 0. So the number of this one is first number. So the power of this one is 0, 1, 2, 3, 4, 5. So 1 into 2 raised to 5 plus 1 into 2 raised to 4 plus 1 into 2 raised to 2 plus 1 into 2 raised to 0. When you add this number, we get 53. Since MSB is 0, it is positive. Now, if you go for the second number, if you observe the MSB bit, the power is 7. And since it is MSB bit is 1, we have taken it as negative number there. When you multiply that, we are getting minus 128 plus 32 plus 16 plus 4 plus 1, which is nothing but minus 75. So in this way, we say that positive number is identified with the help of a MSB bit, or there is a leftmost bit of the given binary number there, because computer understands the binary number. In Verilog code, we use the term signed. Okay, so via signed number, where A and B is assigned as a signed number, which means it can be using positive number as well as a negative number there. Okay, so this is how we represent it in a Verilog program. Now, similarly, let us see the representation of octal and hexadecimal number. Now, first let us see for the hexadecimal number. So here, if you observe 12-bit 2's complement representation of 844 is 001101001100. This need to be converted to the hexadecimal number. We have to group it in terms of 4 bits. Why? Because hexadecimal numbers is of 4-bit representation there. So it is 001101001100. So this particular number is C. This is 4. This is 3. So when you convert this 844 to the base 10 to the hexadecimal number, we get 34C to the base 16. Similarly, another example for the octal number is minus 42. When you convert minus 42 to 2's complement, we have 4 1s 0 1 0 1 1 0. Make a group of 3 bits. We get 1 1 1 0 1 0 1 1 0. 1 7 2 6 to the base 8. In this way, we represent the number in the octal number. Okay, so we can easily convert the binary number to an octal number there. Now let us represent the numbers in the fixed point format. If we take a range of numbers from minus 12.0 to plus 12.0, there are infinite number of real numbers in that range. We cannot represent all of them here, but we can determine a precision of that number. So the precision means what? We are rounding off to the nearest number there. For example, if you choose a precision of 0.01, it means that we have taken after decimal point, we are rounding off to 2 digits. So thus, let us take a simple example. 10.23683 is a number, but when we precision it or round it off to 2 digit after decimal point, so we write it as 10.24. Why? After decimal it is 23, but after 3 it is 6 greater than 5, so we take it as 4, so it is 10.24. Is a representation of this number there. Okay. Now, how this has been converted there, you can easily observe. Since it is a decimal number, 10.24 is equal to 1 into 10 raised to 1 plus 0 into 10 raised to 0 plus 2 into 10 raised to minus 1 plus 4 into 10 raised to minus 2. So this is 10.24. So here what happens? 4 divided by 100 there. Okay. We can easily write it. So 4 divided by 100. What happens? 1 by 25. Okay. Now, similarly, we can write the numbers in binary numbers. That is 101.01 to the base 2. So what happens here is that 101 is 5.0. Observe here 0 into 2 raised to minus 1, because here it is before decimal it is 0, after decimal it is minus 1, minus 2, like this. Now since it is 0 into minus 1, so no value. 1 into 2 raised to minus 2, it is 1 by 4. 1 by 4 is what? 0.25. Okay, so it is 5.25, and you convert it to the decimal number there. Okay, now let us see the number represented here in the decimal number. That is about binary to decimal. The given number is 0.110. It is 6.0010 for the base 2. So here it is minus 1, minus 2, minus 3. Minus 3 is 1 by 8. So the number is 6.125 for the base 10. So this is how we represent the fixed point number with the help of a binary digits there. Now the last part is of floating point. Floating point, which is another representation for approximating the real number, is floating point. How this floating point number? We know floating point and decimal points or anything or exponential numbers. Mathematically we can write it properly, but how the system comes to know? The system comes to know with the help of this particular standards what we have there. One is sine bit, exponential bit, mantissa bit. Now here in floating point, this is the standard format. Okay. Here mantissa is expressed as the fixed point binary number, and the base of the exponent is 2. And the exponent is signed binary numbers, whatever the exponent. Now let us see the examples. Two standards that we have here is single precision IEEE 754 floating point standard. What we have here is, if it is 32 bits, it is a single precision. So one is sine bits, 8 bits for exponential and 23 bit for mantissa. If it is for double precision, it is 64 bits. So it is 1 bit for sine, 11 bit for exponential, mantissa is 52 bits. Okay, so this is how the depending upon the floating point number representation we can choose. Now let us take one example of a single precision. So 85.125, and you convert it to a binary, it is 101.01.001. So what we'll do is that this decimal point is shifted just 1 point here. So 1 point remaining thing. So this part is your mantissa there. Okay, and 2 into 2 raised to 6, because we have shifted 6 points. The decimal point is shifted 6 times, so it is 2 raised to 6. So exponential is 6. So sign bit, since there is no sign bit, what we have specified here, 85, it is positive number, so it is sign is 0. So single precision, what we have is exponential. If you observe, exponential is 8 bits. 8 bits means what? 0 to 7. 2 raised to 7 is 127. 2 raised to 7 is 128. So 128 is represented as 0 to 127. So 127 plus 6 is 133. Convert this 133 to the binary, so it is 140.101. Mantissa, as I said, is the remaining part. So write these numbers here. So sign is 0, 0, 133 we are writing here, and mantissa we are writing, and the remaining thing is extended as 0 there. So this can be written in hexadecimal as 4, 2. So 0, 1, 0 is 4. Okay. 0, 0, 1, 0 is 2. Okay. Next 1, 0, 1, 0 is A 4 000. So this is how the floating point number is represented there. Okay. If you have any questions, go to the comment section, write down your questions, I'll reply to your question. If you like my video, subscribe to my channel, click on the bell icon for further information. Thank you.